Hello and welcome. This is a typical mixing problem. In this case, mixing between two gases, nitrogen and carbon dioxide, in an adiabatic mixing chamber, so there'll be no heat transfer from the mixing chamber to the outside world. And the conditions for nitrogen and CO2 are completely given, and we are asked to find how much is the entropy generation and the final temperature at the end of mixing. This is going to be a somewhat lengthy video because I'm going to solve the problem using two different test steps. One is a binary mixture test step, and one is a general mixture test step because they employ different way of thinking, different procedures. So let's first go and launch the binary mixing test step. So okay, in this window we'll do the binary mixing, and here the general mixing. So you go to the test step page, and we have an open system. We follow the open generic branch, and mixing multi-flow device brings us there. And you notice that we could launch a binary mixture. By the way, the problem asked for ideal gas, so we could use IG plus IG mixture model here, or NIG model, which allows you to use as many gases. But we have just two gases, so then this actually makes the problem solving easier when you have two different gases only. Okay. So let's go and launch it. And we go to the test step page. And here we go. So first let's select the fluid. We have nitrogen as fluid A, we'll assume, and CO2 as fluid B. These are two gases. So this particular app with two gases allows us selection process. IG model has been already selected. So state 1 is already here. We have 100 meter cube per minute, and sorry, it's 100 kPa, and 100 meter cube per minute is the volume flow rate, 100 meter cube per minute, and the temperature is also given to us, 30 degrees Celsius. But most importantly, what is XA? It's pure nitrogen, so XA should not be 0. It should be, its default value was 0, so we should set XA equals 1. X is the mass fraction of A in a mixture of nitrogen A and B. In other words, we have pure nitrogen. To make it pure, XA should be 1. Pure nitrogen, XA should be 1. State 2 will have pure CO2, so XA should be 0, and that's correct. The default value, oh no, it's 0.5, so we better put it to be 0. So now it's pure carbon dioxide. Pressure is same. Temperature is 200 degrees Celsius. And the volume flow rate 50 meter cube per second or per minute. So that should complete calculation of state 2. And now that we know state 1 and state 2, we can find state 3 because we know the mass flow rate. So what will be the mass fraction of A in the mixture? We'll say equals m dot 1 is what is flowing through state 1, pure nitrogen, divided by m dot 1 plus m dot 2. We could do that in the IO panel, but anyway, we have done it here. So the mass fraction, let's just calculate the mass fraction to make sure it makes sense. If you put the pointer over, and you can take a look at this location, it will show you the value of the mass fraction we just calculated. If you put the pointer over, you will see it's 0.665. And if you go back to state 1 and 2 and look at the mass flow that we calculated, state 1, we had a mass flow rate of 1.85 of pure nitrogen, 0.93 of pure CO2, and it should make sense that mass fraction of nitrogen is a little bit higher in the final mixture. The pressure doesn't change. There is no frictional loss in the mixing chamber. We can just put it equal P1. And finally, we don't know the temperature also, so that's all we know about the final state, except we can go to the device panel. we can load state 1 and state 2. It's already set up for a mixing device, as you can see, multi-mixing. And the final state is state 3. And if we set there's no external work transfer, no heat transfer, then you can see that the energy equation should, with Q dot and W dot gone, because adiabatic system, no work transfer, and there is no second exit, so this term doesn't exist. So therefore, we should be able to solve for one unknown, because everything here is known, everything here is known, and even mass flow rate is known. Wait a minute, we did not write the equation for the mass flow rate, so we better go back in state 3 and we write down what is mass flow rate. We should write that down. It should be equal m dot 1 plus m dot 2. So now that we know a little more information, come back to the device panel. We didn't record this, so now it will work. So if we now do a calculate, go back to the device state panels, we'll see the J has been substituted. So doing a calculate will calculate the final temperature. Of course, a super calculate will do the same job, except it will also go back and forth and find the entropy generation. So as you can see, we have already found the entropy generation rate and the final temperature. So instead of doing a parametric study, I want to solve the same problem again, excuse me, and using a different app. And that will illustrate how to use this. So we again go to the same place, but except this time we'll launch the NIG model. The NIG model works on the principle that you create the mixture separately and then calculate the states. And when you create the mixture, in generic problems, all you have to take care of is, the mixture itself. The amount is determined in state panel. So in the mixture panel, the amounts are all relative. So suppose I want to create nitrogen mixture. I shouldn't just care. I should say nitrogen and add it. So we don't know, exactly how much nitrogen is going in this panel. We don't need to know. Mixture B is pure carbon dioxide. So we'll just say carbon dioxide, pure carbon dioxide has been added. So this is pure nitrogen, pure CO2. Could be in kg, could be in kilomole, doesn't matter. Mixture C, on the other hand, we don't know right now the mass fraction of nitrogen or CO2. So we have to wait. So what we're going to do, we go to the state panel and first find the state with mixture A, which is pure nitrogen, as you recall, 100 kPa, and the temperature is 30 degrees Celsius. And the volume flow rate is 100 meter cube per minute. So there is no mass fraction, etc. here at all. This is mixture A, so there is no business of mass fraction. Oh, the temperature got wiped out somehow. All right, here we go. Now we go to state 2. So notice the mass flow rate has been found for nitrogen. That was same as was found in ideal gas in the binary mixture app that we solved. For state 2, we have mixture B. Everything is considered as a mixture, even though we have a pure CO2 here, because this panel doesn't know how the mixture was composed. It just imports all the properties. Now pressure 2 is same as P1. Everywhere the pressure is the same. And temperature, I believe, is 200 degrees Celsius. This is at what temperature CO2 is coming at a volume flow rate of 50 meter cube per minute. So this state also should be calculated. Oh, somehow my pen is going over the temperature and wiping it out. 200 degrees Celsius, because I have a touchpad here. Okay, so now that we know mass flow rate of CO2 and H2O and nitrogen, we can go back to the composition panel and compose the mixture. So how do you do that? Well, in terms of kg, if you think about it, we can say nitrogen, how much is coming in, equals m dot 1. So this much amount of nitrogen comes to the mixture and every second, and equals m dot this much amount of CO2. So the mixture has this proportion essentially. So if we add that, now notice the mixture has been created and the CO2 and the nitrogen mass fraction is 0.665. If you recall, that's the number we got in the binary mixture part also. But this is, I find it a little bit nicer, more appealing way of forming the problem. Anyway, so now that we know the mass flow rate, the composition of mixture 3, state 3, which is mixture C, we can calculate the state equals P1, and final temperature is unknown, but the mass flow rate will be m dot 1 plus m dot 2 from conservation of mass equation. We can do a calculate. So a lot of details property about the mixture is given known here rather than so this is a more sophisticated test step, I would say. And let's take a look at, again, we have the multi-mixing panel. There's no difference here. It's mixing chamber. So state 1 is mixture A, state 2 is mixture B, and state 3 is mixture C. So also we know heat transfer and work transfer are 0. So if I do a calculate now, just like before, we should be going there, and J has been pasted back. A calculate should produce the temperature, and of course a super calculate, or you can go with the device panel, and a calculate should produce the entropy generation rate, which is 0.465 here. And how does that compare with what we did before? 0.465, exactly the same. So the problem has been solved in two different ways, and I hope that gives you an idea about how to use the NIG model and how to use the binary mixture model. Of course, if there is only two gases involved, the binary mixture model makes problem solving a lot easier, the test step easier to work with.